Okay, let's get started. Good afternoon. So you got the email. I sent the email about the homework report. It's also here, right? I want you to just look at the Amazon service agreement. It's sort of similar to all the agreements that you probably signed off without kind of reading about it. But this may be something that you can kind of see what that means. And you can continue with the same project group you had before. But don't try to spend too much time. It's a legal document. You probably won't understand precisely because it's written where you don't exactly understand what's going on, right? It's written by lawyers, for lawyers, not for normal people who agree with that stuff. But just get a sense of what you can gather from it. Because you should have at least enough understanding to sign up for the service, and that's the context. So don't spend time trying to parse the legalese of it, right? I don't know how many of you have a legal background, but if you do, then you may want to put your legal hat off because it's not the intention, right? And I already got 2 feedback on the demonstrations, and if you have any comments, please let me know. And I think one of the comment was to involve more students, and that's one of the things I would like to figure out how to do that. And in the case of that particular demonstration, I couldn't figure out how to involve people, but as we move along, I'll try to involve more of those, right? But if you have any comments, positive or negative, because negative is actually better because hopefully you can improve those things, right? Make sense? So this one, I wanted to cover this topic before we went for the media server, but it's good because now you can get a sense of what is happening, right? So what is the problems that we're trying to achieve, right? So first we looked at the notion of quality of service, right? So we looked at this nebulous notion of quality of service where you somehow figure out what is the service that you want to provide to the user. You have to translate that into every different component to make sure things happen a certain way. And one such component, the main component for multimedia systems, especially the kind that we worry about, which is sent across 2 different machines, is the notion of how the network would behave, right? How the network should have this notion of quality of service. And so if you take a networking class, one of the things that you study about is there are these different layers, right? So you have the hardware layer, some data link layer, network layer, and all those things. And at some point, you stop with something like a TCP or UDP, right? So both of them are designed to send the packets across from one end to the other end. And they're designed to be fair, with other flows, other people who are using the system. They're not designed to care so much about any quality of service, right? So from the TCP networking world, if you have 2 users who are trying to download something, if I can give them equal something, then it's fair, right? And so we want to build some notion of something where we have quality of service. So we know that multimedia requires certain quality of service. So we want to push that concept down to the network, right? And so so we start off with the notion of RTP, which is a standard used by most of the media players like QuickTime or Real or Microsoft Media and all those things. And so they're built, that particular protocol, RTP, is built on top of UDP, right? So from a network perspective, it's not that different from a UDP datagram. But since it's going through RTP, your routers can be set up to deal with them differently, right? So for all practical purposes, it looks like a UDP datagram. For all practical purposes, your router can deal with them as no different from anything else. But you can imagine building a router which now knows that this is part of a multimedia stream, so it can react to something, right? So that's the notion of RTP. Right? So it's built on UDP to give some notion of quality of service to the network, right? And again, the challenge here is we don't want to go overboard. We don't want to, this does not do a reservation and all those things. It just tells the network that this is a packet which has some real-time constraints. Not reserve anything, not go all the way to ensure that your quality is end-to-end and all those things, right? So the protocol for controlling those is RTCP. So what really happens is you're transferring these media streams across 2 players, and those two player and the server, they need to talk to each other to figure out what's going on. They need to figure out how the quality of what they're achieving and all those things. So most of these protocols have a control channel, right, which is what you use to say what's going on. So the server may say, the client may say, you said you were sending 1 megabits per second stream, but I'm only receiving 512 kbps, right? So it can send that information back to the server, and it doesn't have to wait for all the data to go through. So the idea here is you have an RTP stream which purely sends the data, and you do this conversation offline, out of band, through another control protocol called RTCP, and they both look like same 2 different network connections, but one is designed just to control it. So the client can say, I'm only getting 512. The server may send something back to the client to say, if this is what's happening, maybe you should do this stuff, or it can say, I'm going to reduce the quality, and so on. So the chatter happens in a different channel, right? And this is quite popular in data networking, RTCP kind of stuff, but separating the data from the control, because you want the control to go faster. You don't expect too much data to go. You don't expect too much stuff to be happening on the control. You're just saying things look good, things don't look good, kind of stuff, right? And then we introduced the notion of sessions, right? So now you want to build more complex applications, not just sending one stream between 2 client and a server. You want to be able to interact. You want to have, like, for example, a conferencing or something. So the sessions add the notion, it's a higher level concept. It adds the notion of having multiple things. So the server can say, this user is actually seeing from you a video stream, some way to interact with all the objects and stuff. So how do we deal with these conglomerate? We'll see examples of what that is in a little bit. And part of that is the SDP file we sort of looked at. SDP file can be more complicated because it can also say you're going to have multiple streams. How do you treat the different streams, different contexts in the same thing, right? And again, another important aspect is the voice over IP. I kind of mentioned that before in some sense. The idea here is, rather than having a telephone lines, hardwired telephone lines, the future looked like it was going to be voice over IP. I'm not sure what the future is at this point, because most people are moving towards cellular phones, which sort of circumvents this whole issue, right? The problem there is, if you look at most of the offices in a building, you're going to have your Ethernet data going to all the desks. You're also going to have your PBXs connected to a phone lines, right? So for each desk, you have to maintain this 2 different infrastructure, right? And the phone infrastructure, you have to maintain the separate aspects for it. And there are some nice things about the phone infrastructure, right? One is it's sort of guaranteed. Once you have the line, you get what you want. The other thing is it's incredibly wasteful, right? Most of the time, it's not sending too much data because you're just talking on the phone. And when you move your desk or something, I need to move all the stuff. I need to go configure these things. If any of you configure these PBX systems, they're horrendously complicated because they're designed to sort of be deployed and work and everything. But if you want to move and everything, it tends to be pretty complicated, because it's basically when you make a call from here to someone, in some sense, you're having a dedicated line from you all the way to the other person, right? So you have to maintain that kind of stuff. So the observation here was, since everybody has an internet connection to their Ethernet connection to their desk, right? Why not use that to send the telephone call? So you're changing your telephone from some sort of from telephone to some sort of like a video, audio chat, right? And you still want it to look like a normal phone. You still want to have a number and all those things. But now it's sending datagrams, right? So what that means is, I can take if I had an office phone, I can bring it over, okay, connect it to this one here. And if my phone can authenticate itself, if my phone knows who I am, right? So if I put it here, then it looks like I'm here, right? So no one would know any different, right? It's very similar to how your cell phones work, because essentially when you move across, your cell phone will keep telling somebody at your provider to say that you are right now here. So if you move from here to, say, travel to Los Angeles, at LA, you'll be talking to a base station, and your base station knows you are there. So they basically route your calls to wherever you are, right? But the technique is sort of the same, but the voice over IP would mean that you now treat everything as an audio chat, right? There are a lot of benefits to it, which is I don't have to have dedicated bandwidth for it. It depends on what you're using at this point. There are a lot of negatives because the quality of service is not guaranteed anymore, right? you don't have reserved bandwidth across. So if I connect my phone here, then I'm competing with all of the other folks here, and so I need quality of service. The service I was used to, I can no longer get, so I may run into trouble and all those things. So we'll see how you initiate the calls and how those things work. And again, it's session announcement protocol, sort of like the STP-ish kind of notions on how to announce what's going on in the multicast sense. So those are things I would like to discuss today. And so RTP is pretty popular. You would have used it if you used any sort of streaming like QuickTime or real Microsoft Media, or any of the other schemes that you would have used, right? So if you went to the preferences menu, you'd have seen that it's using, it'll ask you, do you want to use RTP, RTSP kind of things, and so that's the notion, right? So it's built on top of UDP. It's not any different from UDP, except since you pronounce it as a RTP, people can deal with them differently, right? What that means is, as a UDP datagram, UDP means that from a networking perspective, UDP is a datagram. It's a best effort, right? So there's no guarantee that it'll reach another end. So what it means is, if you have two clients communicating with the UDP datagram, the network will make every effort to deliver it on the other end, right? But it makes no guarantees that it will be delivered. It makes no guarantee that it will be delivered in order. So if you send 3 packets, they may be delivered in any order. Some of them may be dropped. Some of them may be duplicated, right? So you may get whatever you get. So you may get 1 copy. You may get more than 1 copy. You may get 0 copies, right? And it may come in any order. So you still have those guarantees that the network provides, but now it can treat them differently because it knows it's a RTP. So one of the things I can do is, if I know it's a real-time data and I have to drop something, I can drop sooner now because I know that as a UDP datagram, I can delay it for a long time. But if it's a RTP datagram, then I may drop it sooner because then somebody can react to it rather than me waiting for it later, right? So it's used by these different applications. Right, so in terms of if you look at the network protocol, this is, again, if you take networking class, you'll worry about it. So essentially, the network protocol is defined as certain layers. Each layer is built on top of the other ones. So at the bottom, you have the physical layer, which deals with the cables and the frequencies that you operate and all those things. Then you build a protocol like Ethernet or Wi-Fi or something on top of it. Then you build the internet protocol, and you build UDP on top of it. Internet protocol is the one that gets routed around the world, and UDP datagram lets 2 applications talk to each other, right? Internet protocol, if you think about it, it essentially allows 2 machines to talk to each other, and UDP lets 2 processes to talk to each other, right? And RTP, RTCP essentially it does the same thing, but it gives you a little bit more control, right? So if you do a TCP dump, right, it will behave no different than UDP datagram, right? And again, the control is the RTCP. So if you look at it from a block diagram perspective, when you have the application, so if you have 2 applications talking to each other, right? So they send the data. So this is the server, this is the client. The server would send the data as a RTP datagram to the client, but the client would communicate back to the server to the control protocol, right? So it can say things like pause or play and stuff like that, right? So it can have this communication, right? So why would you separate these 2 things out? What do you gain by having a separate control channel rather than 1 channel? From a network perspective, it doesn't really matter, right? Because you can write whatever, and then the other stuff can go, right? What would you gain by separating these things out?
Yeah. Having a separate control channel gives you better quality of control over the quality of the service?
In what way?
Well, you can communicate across the network to say, yes, I received a message, or no, I didn't get that message, try again, or things like that.
But you can also do it with the other mechanism, right? So let's look at, let's say you have this. This is a server, this is a client, right? And let's say the server is sending lots of data packets, right? The way so this is using RTP, and it's also using, let's say RTCP, right? It's sending these data, right? So this is what it's doing right now, right? Do you expect a lot of traffic on the RTCP channel? How much volume would you expect? Like, would they be the same? Would RTCP be more? RTP be more? Yeah.
RTP be more. So that's the actual data.
Yeah. So this would be a lot more, right? So if you're sending like a 1 megabits per second, right? Let's say. Sending 1 megabits per second, you're hardly getting any data here, right? It's few maybe bits per second, right? But technically, you can send. Let's say this is control packets, right? These are data packets, right? I can send them here, right? Sending them twice over means really nothing on the network, because from the network perspective, you're going to still see all these packets, right? You're not going to get any advantage by separating these out. So you still get to, if the network can only support a certain amount of traffic, you only get a certain amount of traffic, right? So what do you gain by, why don't you want to do this? I think you're on to the answer, but what's a specific reason? Yeah.
I guess it's supposed to be a real-time thing, and sticking random packets in the stream could upset things.
Yeah. Yeah. So if you're doing some kind of real-time stuff, right? The control may affect the way things are being played, right? Or maybe not, right? So depending on how much the traffic is. If this is 1 million bits, and then you add in like a few bits for control, right? You don't expect this to throw off the flow, right? But it might, right? Yeah.
Are these two separate network lines? I mean, do you have one network line dedicated to the control stuff?
No, you don't, right? So even though I draw out like two different lines, from a physical perspective, there is only one link, right? So if you're using wireless, you have one wireless network, right? So these are two different network connections between two machines. So this may be, if you look at here, this may be an Ethernet, right? But they're two different connections, right? So conceptually, you make it look like these are two different things, but physically on the wire, they would go something like this, regardless of how you look at it from the UDP perspective, right? Because there's only one wire, so they're all interleaved, right?
So would this be at all similar to if I opened up my laptop and opened up two terminal windows and typed in each terminal window SSH to my desktop?
Yep, exactly. Yeah, so if you use two SSH, or when you go to a server, a web server, and you're downloading images and stuff, right? So all of them are being downloaded. So if you go to a normal web server, images and the HTML come to you on separate links. On the wire, they'll all be the same, right? But conceptually, you are requesting on different network connections, right? So where would this, yeah?
So does the UDP or the TCP that it's based off of try to treat both connections fair?
So that's sort of where the answer is, right? So on the network, they're no different, but potentially your system would treat them separately, you treat this as separate connection from this connection, right? So what happens is, when you see something like this, right, you're kind of having like a train effect, right? So you have all this traffic jam with all these packets going through. So your little packet to say, so for example, this may say stop listening to the stuff, right? Stop this transfer or something, right? But it has to wait on the wire, right? If you as application are mixing both the control and the data onto the same particular connection, then no one else knows that this is not as important as this one, because this basically says stop whatever you're doing, right? So you would like to send this, we call out of band, and not sequentially, right? So having two connections sort of give you that, right? So when you have two connections, then hopefully this is the control is sent separately, so it can sort of get ahead of the line. So even though the server is sending lots of data, you can imagine putting the control in front of the stuff. But essentially what you're trying to do is, this has higher priority than the data, right? The data, you want to keep it flowing, and sort of what you pointed out, you want the data to be flowing at all times, but you also want the control to jump ahead of the line and move forward. And one way to do that is to have separate connections. It also keeps the stuff kind of clean, right? So when you build these routers, you may decide to keep the RTCP much higher priority than even RTP, because you know that RTCP is essentially a control protocol, right? So if you want the control to work faster, so if you're streaming something and if you press the pause button, you want this reaction to be faster. If you're a client and you press the fast forward, you want the information to go to the server faster, right? So I could change my router to say, if I know it's RTCP packet, get it moving faster, because A, that it's probably important because it's going to control something, and B, it's not expected to send lots of data, right? So since I know it's not a lot of data, I can treat this differently than the RTP data, right? Other than that, there's not really much of a difference, right? So you can try playing with this stuff if you're more confident with the networking capabilities, right? One of the ways you can look at that is if you go to any of the media players like Real or all those things, they let you choose the port that you want to use for RTP and RTCP, right? So for example, they may say this will be in port 5000 and this will be in port 5001 or something, right? There are some standard ports and there are some ports that you can change, right? So if you're confident with setting up firewall rules, right? What you can do is you can start streaming something and use a firewall to block this off, right? Basically drop the packet. You'll still see the stream coming, but you won't be able to control it. You won't be able to stop. You'll be able to stop by killing the player, but you'll lose the communication back and forth, right? It'll look like it's still moving forward, but you'll very quickly realize that the client is now flying blind, right? The client, if you look at TCP dump data, you'll see the client will start saying something like, Mayday, things are not going well. You can muck around the stuff, but none of them is actually going to the server. Server will constantly keep sending something. So if you're sending lots of data, the client would say, "You're sending too much data for me. Back off." But if you sort of kill this the feedback channel, then it'll still continue to work. The server will continue to send data, but the control feedback is not there, right? So that's one way to see about how these things are reacting, right? So so essentially what you're trying to do is you're sending out of band data of the RTP flow. So you want to send it at a higher priority ahead of all the buffering issues, because you want the RTP channel to send the data in how it wants to do, and he wants this to be faster. And the client may send this periodically. It depends on how the client is behaving. So it may send every so often, or it may only send when things change. It gives feedback on the quality of service that is experienced by the client, right? Because one of the problems with the networking model is when you are a server, when you're sending some packets, you may not get the feedback of what is happening on the network till somebody tells you what's going on, right? So I, as a server, may be able to pump in 100 megabits per second video, but somebody has to send me feedback that something is being dropped, right? So in this case, if the server was to tell the client, I'm going to send you 100 megabits per second, and if the client is only seeing 1 megabits per second in the long run, so it can basically say, I'm only getting 1 megabits per second, right? So that may mean that you're sending too much more data than what the network can support. That may mean the server can ease up on how much it's sending, because even though it doesn't change any of the stuff, the server can be a little bit nicer by sending 1 megabits per second. So they chat about those. And hopefully once they settle down on the stuff and nothing else changes, the amount of feedback would be minimal, right? So it can send you things like the byte send, packet send, last packets, and jitter, right? So jitter is another metric that is sort of hard to describe, but the idea here is if you're sending a packet, let's say if this is time, right, and you're sending these packets in certain fashion, which means that the delay between the time between these packets are something like this, right? The notion of jitter is if on the client I receive these packets like this, right? You are noticing a lot of jitter, right? You want the client to receive it sort of in the same delay between the packets that you sent, right? It's okay if the first packet comes here. So the latency between when the server sent it and the client sent it may be large, right? That's not what we're worried about. What we're worried about is after the first packet was received, what is the time delay between those packets, right? If it is the same, then you expect 0 jitter. But if it changes often, so if you see that one is larger, some of them are smaller, then you see like this, right? So the first packet came here, the second, third, and fourth packet came all close together, and then there was a longer gap, right? So you're seeing lots of jitter, right? So the server can say, this is sort of how I'm sending these packets, and the client can sort of see how it's getting the stuff. And it's kind of hard to define because you only worry about when things begin to affect you, right? So if this was sent in 10 milliseconds and you received it at 10.1 millisecond, the player may not care because it may be able to stream without loss of quality. But if it tends to be large, then it can send a feedback saying it's higher jitter back after, right? So it sends all the information back. So it sends information about how many bytes I received, what's the loss, and network conditions, sort of the feedback. Server needs to figure out how to change what is sending, and the server can use that to react to it. And as you can see with the experiment I mentioned before, you can block those packets, and the server would continue to send it whatever it was sending before, right? And there's several types of RTP, the RTCP package, essentially, which tell, which is whether it's a sender report or the receiver report, and different kinds. It's not encrypted or what have you, so you can inject some packet into it to make it look different, right? So for example, I can inject a packet to say, tell the server stop the transmission, right? Because one of the packets you can send is the goodbye packet. So if I can send a goodbye packet, then the client would be disconnected, right? There are protocols to deal with those, but for the most part, that's not a very important thing. The goal is they're communicating. Security is not a main goal here, right? In the RTP itself is mostly sending data for the particular stream, right? And it will have all the stuff that it needs to do. So it's a UDP packet, right? But it has a little bit more information for multimedia perspective in terms of time monitoring and stuff. So it can timestamp the time it was sent, so the receiver can look at that to see how it's receiving, right? So if it says that this was sent at time 1, 2, 3, and 4, and here you receive it at 10, and then you receive it at 10, like 12.5, then I know that the time that was sent was not the timing that I'm receiving. So you can detect something with it. Right? The server may add sequence numbers, so you know when there's error, right? when things are lost. The server can add sequence numbers so you know when things are received as a duplicate on the other end. And so there are other things that you can add to this stuff to make it more useful as a media stream. But one thing to remember is multimedia streaming systems were aware of networks which are not well behaved, right? So they are usually resilient to all this stuff, regardless of whether you get the feedback from the RTP layer or what have you, right? You like the multimedia streams to not depend on the prior and the future packets because you expect things to be lost. So in general, they are much more resilient to this stuff. So even if you lose a packet, even if you receive the packet twice, there are some errors where you don't have to worry about it, right? So if you receive the packet twice, maybe you'll draw the same block twice, which will be ignored, kind of stuff. So in general, they have to be worried about the concept because they're always operating on a condition where they want as much resources as you can give them. And when you're pushing the network to that level, you always run into these kind of issues, right? Again, it depends on the particular kind of service that you're using. So QuickTime may not use all the facilities because it may not care about this stuff, right? And there are other services that are added that are part of RTP, which add more service, which provide better quality to the system. So for example, you can have a mixer service which may take a couple of inputs, right? And it may bunch them together and send them across at the other end, and then unwind them on the other end. So if you have multiple audio channels coming in, so each of the audio channels may have come in every 20 millisecond packets, but you mix them together, create a larger packet, which is sent on the wire without any of the constraints that you would tend to notice. Right? So you may see one audio stream sending packets every so often, another audio stream sending packets every so often, right? You may collect these two packets and send them off in, let's say, 2 packets back to back, and on the other end of the mixer service, you demultiplex them, so you kind of split them up separately, right? The way you do that is, it's in the network sense, it's better to send larger packets than smaller packets because the overhead of sending small packets is fairly large, right? So you may collect all these stuff together and then send them across. So you're not really trusting the network to do all the services for you, right? And translator services would change some things along the stream. So it can change if you're having a high quality stream, you can change it to a low quality stream, and so on and so forth. So again, these are services that can be added because now it knows that these are multimedia streams. Now it knows that there are timing constraints. So I can do stuff to make it better for the network, but I have the ability to get back what was sent, right? And that's the point of these kind of added services. As part of the stream establishment, you kind of say what kind of a stream it is, and for example, it's a MULA audio encoded or H.263, a JPEG, a MPEG, or whatever. And so the service, the mixers and translators can respond to that and treat them differently, right? So that's the notion of RTP and RTCP, right? So here you're adding this little bit added service. You don't want it to be the full media server, but you want to have some notion so that the network can do something for you, right? You still have the media endpoints, the server and the client, reacting to things better. So if the network drops really drastically, then it's up to the server to change whatever it's sending, so the client can still receive it, right? So the next notion is the notion of sessions, right? And we'll see more of that when we talk about collaboration systems. And you may have seen some of this stuff when you're talking to YouTube, right? So when you look at YouTube video, right? These days you see annotations, right? You see advertisements coming on the screen. You see like some link to some pages and all those things, right? So essentially, you can think of this as you're building a session with all this stuff, right? So you're building a session where there's a video in the background. There's an advertisement video here. There are links here and so on, right? So when you watch this video, you're watching this session, right? So from your perspective, you're watching the session, you're not really worried about all these different components. But from a system perspective, there are all these different components, right? So there is this video which is happening independently, there is this advertisement which is happening independently. If it's built right, so they will have to be sent separately to you. The notion of session manager is to make sure that I have a way of managing all this stuff, right? Meaning, I, as the one who's designing the system, may say, this particular screen will have a video, will have an advertisement stream coming in as a video. It will have to be, this video and this video will be overlaid on top of each other at the player, right? But from the manager perspective, I may say, if the network quality is going downhill, right, I may want to give more priority to the advertisement than for your video, right? So this is a way for me to treat all these objects which are part of this one particular aspect that I'm trying to do and managing the priority of those, right? So this is a higher level concept. So far RTP and RTCP is between a single server and a client, right? A single entity that is being streamed. Now I'm trying to see there are multiple entities here. And so in this particular case, there's a whiteboard, there's a video, and an audio. So how do I deal with the network bandwidth across these three, right? Because if I don't do this stuff, I can treat all of them equally. I can treat all of them equally and let the network deal with those. So the network does not know what is important, right? So for example, if I had a video and audio stream going through, a video will have lots of packets, and audio will have very few packets, right? So if you're trying to be fair and want to give each one of them equal stuff, you may end up giving audio a lot more quality than what you might have wanted, because the audio may be going at 100 kbps, video may be going at 4 megabits per second. So the network may say, I'm going to give each of you 200 kbps or something, right? The notion of session would mean that there's way to express that there are these two stuff and things are going downhill, and so the client can say, I'm experiencing loss, and then the session management can say, so redirect the amount of traffic being sent on the audio channel, right? So the server will back off, even though it could send more data, just so that it can give more of a chance to the video, right? And that's the notion of the session. Does that make sense? So it'll become more and more easier when you go into more complex systems, right? So one of the complex projects that which use this session kind of stuff is video conferencing and audio conferencing, right? The notion here is when you have I don't know how many of you use the thing called access grid. So if you go to a CRC building, right when you walk in, you'll see that there's a bank of computers and stuff, right? I think that right behind it there is a access grid to do a teleconference, telepresence kind of systems, right? So the goal is not to have one camera and one video kind of stuff, but multiple participants with all the videos and audios and all those things. And if you go behind the room, there's a projector room, there's a human technician who's sitting there who's trying to see how to mix these different streams to make the whole thing happen, right? And session is essentially something like that. They're trying to see how much to give to each of the video and audio and all those things, right? So one of the demos for this was, there was a project out of USC. They were trying to have I think 24.1 stereo, right? So if you look at the DVD, you get like 5.1, and if you look at the Blu-rays, you get 7.1, right? So essentially, you have 7 speakers and the subwoofer kind of thing. So they wanted to do 24.1 stereo concert across a long distance, right? So they want to have, let's say, a pianist in Miami and a cellist in New York, and the audience in Los Angeles, right? They want to have this concert across the planet. They need a 24.1 because the people who are sitting in Los Angeles need the ambience of sitting in a concert. So you want as many speakers, as many quality and all those things. So if you're trying to do those things, and of course you want to have video to see what is being played, it's not just the audio kind of thing. So now you have all these streams coming from different locations, and how do you express what is going on, how to manage those things is the notion of session, right? It's easier to sort of see what it is than to express it and then to manage it, and that's the ongoing sort of research thing. Right. So there are a lot of things you have to do. So you need to figure out who belongs in this thing. So you need to figure out whether this particular session belongs in this stuff, right? Whether this particular audio is a member, has to be able to control. We need to monitor what the workspace is. In the case of the concert, the workspace is the concert hall, right? So I want to make sure that everything is how they should be. I want to coordinate these things. I want to make sure that the timing between those streams are set properly, right? So in the case that I was explaining, if the pianist who's in Miami was singing for somebody in New York City, right? So it turns out when these people are playing, they look at each other to get cues on where things go. It's not like they're a machine. They're singing independently, right? So they have to have some sort of feedback of where the other player is, so they can change their timing, right? And the people who are watching this there's an implicit notion of what these timings are to be, right? So when you don't notice it when you are in the hall, right? But you sort of expect that if I'm talking and you're in the back, somebody in the back should hear it lower volume at a little bit later time than somebody in the front, right? And we all know this stuff because when I talk here, I know what the distance is. So when I ask some question, it takes some time for the question to travel in the air and stuff. But that's all sort of, I mean, we do it every day, so we don't actually worry about what's the timing delay and all between these kind of stuff. But when you're doing across the planet, when there's no physical somebody here, things become a lot more trickier to manage all the stuff, and that's the hard part, right? And it's important not for the, I don't think we're going to have concerts across the planet, but the notion of having conference calls and conference stuff would be tremendously useful because you spend so much time traveling and stuff, and if you can do all this stuff in a seamless fashion, that's a really good thing, right? So to control, you need to figure out what the session names and numbers and all those things. So if any of you have done any kind of conference call in companies, right, WebEx, and I think Nahrstedt subscribe to WebEx and all those things, right? So you might have been given a session ID, you might have given a session ID to join a conference call and all those things. And essentially, those are the things that we worry about. And we have to worry about the conference control, right? The conference control problem is essentially trying to figure out who should talk, right? So in this particular classroom, if all of us talk, right, at some point it's useless because everybody is, we cancel each other out. So what we really want to do is when I'm talking, somehow I need to give control from me to somebody or whatever, right? In real systems, those are sort of easy. I sort of look at you and I see that you want to talk or something, then I give time to you because I can see the feedback loop is pretty good. In these kind of systems, things become very hard. And another time we don't actually do remote class lectures, right? When you have the remote class lecture systems, you run into this problem, right? So suppose you are all in a different building. For you to sort of raise your hand and say, I want to talk, right? The delay comes into the picture, right? So like I mentioned here, it may be the case that what I'm saying may come to you 2 seconds after I said because you don't know any different. Because if you're in a different room, 2-second delay, you wouldn't particularly care, right? But when you want to raise your hand, right, it may reach me like after 3 or 4 seconds, right? So, and then you run into all the problems. So how do you give the control, the conference control, the pass the baton across the different users? It seems like a simple problem. It's extremely tricky because to get the timing right is very hard, right? And the whole sort of other stuff, the configuration, how to figure out the quality of service, especially when you have multiple participants. How do you make sure that somebody who's not getting good quality can still participate? How do you make sure that, say for example, you're on a wireless network, so I'm going to give you less video, more audio, absolutely high whiteboard versus somebody else, that sort of a thing. And how do you add users? How do you group membership and stuff? And if any of you have done those things, you notice that it's a really pain because you get this email with all these instructions which you have to exactly follow. But what you like is a more seamless kind of a feeling, right? So the sort of the overarching theme for that is the notion of RTSP. Again, it's a session protocol. It's built on top of RTP, RTCP. It controls multiple. You can think of it as it controls multiple independent RTP, multiple RTCPs. And again, you may use it, it may be built on top of UDP or TCP or what have you, but conceptually it's a higher level. It controls multiple RTP sessions. So here's illustration of what's going on. So you may have the RTP, RTCP going through, but RTSP is controlling how much should go to the audio, how much should go to the video, and how they should be synchronized and all those things. And there are certain certain parameters that the protocol supports. I'll let you look at that. Essentially, to start and stop the sessions and control the sessions, the semantics are added, right? And there are certain extensions for those. And the SDP that we looked at in the class is sort of the simplest case of RTSP, right? In the SDP case, you're only looking at controlling two different in audio and the video stream. You can also add a little bit more stuff, HTML and all those things. But essentially, you put them into a file which describes what the session is, so the endpoints can manage the sessions, right? And it has a lot. It's a lot more powerful than what we looked at, right? It can describe all these things of what kind of session is going on, and all those things. We're not going to go through the details. I mean, we saw something like this, right? So if you look at so essentially it changes for the different kinds of session that may be happening. But essentially that's a way for both the client endpoints to say what they were doing. Now you need a session manager which kind of maps all this stuff, right? So the last one is the voice over IP, right, which I kept mentioning. So we were supposed to go to voice over IP for the whole campus, and I don't know what happened. It kind of stopped. You might have seen these kind of phones in this building. So if you go to one of these buildings, you see people having this kind of a phone. Especially, so essentially you log into the phone. The phone is your phone, right? So if you take the phone out and then plug it anywhere else and you log in, you get to make phone calls, right? It's pretty nice because then we can get rid of all the voice links and stuff, and it has other features. Then I can, since it's all digital, right? So I can have voice, conference calling and voicemail and all those things fairly easy and stuff, but because nothing is reserved on the line, right? So we can get rid of the stuff. So that's that's the particular call. You may have seen software applications for it, software voice over IP applications for jailbroken iPhones or laptops and stuff like that, right? So the thing that we want to worry about here is the notion of signaling. Signaling is the notion of calling somebody, right? So the telephone ring model. So if I want to signal someone, I need to know who you are, right? So in the case of the old phones, when I signal someone based on the phone number. And phone number, I essentially tell the system that I want to call a particular phone number, and all it knows is your home is the endpoint for the phone, right? So it will direct the call from you to your home, right? So I call my telephone operator here, who eventually finds out where my home is, where the correct endpoint is, and they send the call to the home, and then your phone rings, right? I'm not accessing a particular phone. I access anything in my home. So all the phones in my house ring because I'm essentially calling my house, not me, right? Whereas here, I don't have the stuff. My endpoint is the phone, the physical phone that you're carrying. So that means that you have to get yourself a name. You can use your phone number as the name, but somehow you need to have a name, right? And so the signaling is a problem of how do you figure out those things. So you figure out what the name is. Then I figure out I have to know your name or your phone number, right? Then I have to call you, right? So calling you would mean that you cannot do what you did before because I'm not calling a house. Houses rarely move, but people or these things tend to move, right? So whenever you move, you have to tell someone where you are. So you need to have a location server which knows where you are all the time. So when I make a call, I would maybe call Notre Dame server, which tries to find where you are. It may ask location server. It may ask other SIP servers. Eventually, it will find where you are, and then we communicate with each other. And once you start to communicate, there are a lot of things you can do. So we can, since it's internet-based thing, we can bring all the multimedia technologies we talked about, right? None of these things did not matter when we didn't have these kind of phones. Like for the normal phone, The telephone company may say, I'm going to send you bandwidth from 100 to 4,000 hertz. It doesn't matter anything else after that. I don't have to optimize those things. But here I can optimize this stuff because I'm sending on the internet. So I may be in a cafe where I don't have enough network bandwidth. So I may do silence detection. So if there's no conversation, I may detect silence and not send any data. So we need to negotiate between those two endpoints. So my phone and your phone talk to each other. And they figure out that I'm going to send MPEG for audio, and I'm going to do voice detection, all those things. And we agree with it, but that particular protocol can be managed. And then we start the conversation, right? And the protocol that is pretty popular is the SIP, right? Succession initiation protocol. And it's I think I have a. So within SIP, your user can be called a phone number at gateway or an email address. And so essentially, if I want to make a phone call, I'm going to take an extra minute. So if I want to make a phone call, I call my SIP server, and it may forward the request at some point, asking location server where I am. It may say, oh, John Smith is actually at this particular location. And so then you talk directly amongst each other. Right? So in the SIP sense, the server is only involved till these things happen. And once the connection is established, it's a peer-to-peer. Your phone is directly talking to somebody else's phone, right? And this redirection, which happens the same way. The server may say, "Don't talk to me. Talk directly to here." So I'm not involved at all, right? And so these are the different protocols. So you think of them as the ringing thing. So I do an invite, meaning I want your phone to ring, and then you can acknowledge saying you are there. And when you're done, you do a bye, and then you break the connection, right? And so we are out of time, but essentially SAP is the session description for multicast, right? So its upcoming protocol is not as popular as the other ones. Right? That's about it. We'll continue on Friday.